Hi, welcome to 5111 practice exam session. My name is Hyunsuk Yu, one of your TAs, and today I'll be solving question 3 in your practice exam. So, question 1. You have to calculate the electron configuration for the boron atom in the ground state. So to solve this question, you have to know that there are 5 electrons for the boron atom. So those 5 electrons fill up the lowest possible energy orbitals, and that is 1s, 2s, and 2p. So we know that 2 electrons can fill up one orbital. So 2 electrons fill up 1s orbital, 2 electrons fill up the 2s orbital, and 1 electron fill up the 2p orbital. Now part B. Sketch the RPD for the excited electron that has the principal quantum number of 20 and the angular quantum number of 19. So to graph RPD, you use the fact that there are n-1 nodes where the total radial nodes is n-l-1. So if you plug n and l into the formula, we can see that there are 0 radial nodes. So we can infer that RPD of this excited boron electron would look very similar to the 1s orbital of the hydrogen atom. So it would have a peak in the middle, and RPD would converge to 0 as you increase R. So note the difference between RPD and psi squared. So RPD is a function that is 4 pi r squared times psi squared. So we know that as you increase, as R goes to 0, RPD goes to 0 regardless of psi squared, because 0 times psi squared is 0 regardless. So we can see that RPD always passes through the origin when you plot against R. Now, estimate Z effective for the excited electron in the boron atom. Now to solve this question, you use the fact that Z effective is equal to Z minus S, where S is the shielding constant. And shielding constant is a measure of how effectively the inner electrons screen the electron of interest from feeling the actual charge of the nucleus. So that means that if the electrons screen the electron from being attracted to the nucleus, it would have higher shielding constant. And for this excited electron, it is very far away from the nucleus. N equal 20 means that it's very far from the nucleus. And if it's far from the nucleus, it means that other electrons are likely to come in between the excited electron and the nucleus, thus effectively shielding the excited electron from feeling the actual charge of the nucleus. So Z effective would be the charge of the boron atom, which is 5 minus 4, which is the number of inner electrons. So it will be equal to 1. Now part B. You're given that you shoot an X-ray into some atom and you find that there are 10 distinct peaks. So since there are 10 distinct peaks, you know that there are 10 different orbitals for the given atom, right? And you find the 10 lowest orbital, So 4, 5, 6, 7, 8, 9, 10. And the atoms that have the final electron filled up in the 4d orbital is the so-called 4d transition metals, which are the elements, these 10 elements. Now, you determine that electron with the lowest kinetic energy has the effective of 41.13. And from this fact, you have to eliminate some candidates for the unknown atom. Now, Z effective has to be greater than Z because Z effective is Z minus S, and S is greater than 0. So if you plug in Z effective into this inequality, you know that Z should be greater than 41.3. And since niobium, zirconium, and yttrium has the effective that is, Z that is smaller than 41.3, we know that these 3 atoms cannot be the unknown atom. Now, you have to calculate the binding energy of the electron that experiences Z effective of 41.13. So, we were given in the previous part of the question that this electron has the least kinetic energy. And in order for the electron to have the least kinetic energy, it must have greatest binding energy. And the electron with the greatest binding energy are the electrons in the 1s orbital. So, we use the Rydberg equation and plug n equal 1 and Z effective 41.13. If you plug it in, you can find that the binding energy is equal to 2.30 times 10 to the 4 electron volts. Notice the use of sig figs here. So since there are three sig figs for the Bohr constant, I used 3 sig fig for the final answer. Now, what is the kinetic energy of the electron that is emitted by the X-ray, which has a wavelength of 0.0505 nanometers? So you know that kinetic energy is equal to the energy of the photon minus the binding energy, which is also denoted as psi. Now you plug everything into this formula. So Planck constant is 6.626 times 10 to the minus 34, and the speed of light is 3 times 10 to the 8, and we know that 0.0505 nanometers is times 0.0505 times 10 to the 9 meter. And you plug in the binding energy that you found in the previous part after you convert it into joule. So joule, so second cancels out, meter cancels out, EV also cancels out, and you end up with the kinetic energy in joules. So that's it for problem 3, and everyone good luck with the first exam.